In 2022, the James Webb Space Telescope captured images of galaxies that formed when the universe was barely 2% of its current age. Galaxies massive enough to break the model built to explain how they could ever form at all. Webb found black holes that outweigh their own host galaxies by 300 times. It detected oxygen in a galaxy born just 290 million years after the Big Bang. Proof that entire generations of stars had already lived and died before we thought the very first one had even switched on. And it deepened a crisis around the most fundamental number in cosmology: how fast the universe expands. A crisis that still has no answer. The most unsettling part isn't how far Webb can see. It's what these discoveries reveal about how wrong we were, and how that uncertainty now reaches all the way to how the universe may end. On December 25, 2021, a rocket lifted off from the northern coast of South America, carrying the most complex machine humanity had ever sent beyond Earth. Folded inside its nose cone was the James Webb Space Telescope, a 6,500-kilogram instrument built not to replace Hubble, but to see something Hubble physically could not. The difference starts with the mirror. Hubble's primary mirror measures roughly 2.5 meters across. Webb's measures 6.5, built from 18 hexagonal segments, each coated in a thin layer of gold, locked together into a single light-gathering surface more than 6 times larger than its predecessors. But size alone isn't the real story. Hubble was tuned to ultraviolet and visible light, the same range our eyes can detect. Webb was built almost entirely for infrared wavelengths, stretched far beyond what human vision can register. That single design choice is the reason everything that follows was even possible. Getting the telescope into space was its own kind of miracle. To fit inside the rocket, the entire structure had to be folded. The mirror, the sun shield, a 5-layer heat shield the size of a tennis court compressed down to the size of a delivery van. Once in space, it spent the better part of a month unfolding itself, piece by piece, with no astronaut on hand to fix anything that went wrong. Engineers had counted roughly 340 individual steps in that sequence, where a single mechanical failure would have ended the mission permanently. Webb wasn't heading to low Earth orbit, where Hubble lived and where astronauts visited 5 separate times for repairs. It was traveling nearly 1 million miles out to a gravitational parking spot called the second Lagrange point, far enough that no rescue mission could ever reach it. If something had snapped, it would simply drift there, finished for the rest of its existence. Nothing snapped. Every fold, every latch, every one of those critical points held. By mid-2022, the mirror segments had aligned to a precision finer than the wavelength of light passing through them. The instruments had cooled to nearly 230 degrees below freezing. The telescope was ready to listen to a part of the universe no instrument had ever heard from directly. To understand what it was listening for, you have to understand what happens to light on a 13 billion-year journey. As the universe expands, the space between a distant galaxy and us stretches, and the light traveling through that space stretches along with it. A photon that left its source as ordinary visible light can arrive at Earth shifted all the way down into the infrared, simply because the space it crossed has grown so much in the meantime. Astronomers call this redshift. The farther back you look, the more extreme it gets. The very first galaxies, those that formed within the first few 100 million years after the Big Bang, emit light so heavily redshifted that by the time it reaches us, it isn't visible light anymore. It's deep infrared. And for most of the history of astronomy, that signal went completely unread. It isn't only distance that hides this light. It's the universe's own early history. In its earliest stages, Space was filled with a fog of neutral hydrogen so thick that light couldn't travel freely through it at all. Only once the first stars and galaxies switched on, flooding their surroundings with ultraviolet radiation, did that fog begin to burn away, clearing a path for light to finally travel uninterrupted. Astronomers call this transition the epoch of reionization. It's the exact period Webb was built to look directly into, watching the universe shift from opaque to transparent, billions of years after the fact. Earth's own atmosphere adds one more obstacle, absorbing most infrared wavelengths before they ever reach the ground. The only way around all of it was a telescope cold enough, large enough, and far enough from every source of heat in the solar system to catch that ancient signal without being blinded by its own warmth. The first real proof that it worked arrived on July 11th, 2022, in a single image of a galaxy cluster roughly 5 billion light-years away. The cluster itself wasn't the point. Its enormous mass was being used as a natural lens, bending and magnifying the light of galaxies sitting far behind it, ones that would otherwise have been too faint to detect at all. The resulting image covered a patch of sky no bigger than a grain of sand held at arm's length. Inside that grain were thousands of galaxies. Some were stretched into smears and arcs by the gravity bending their light. Others glowed faintly red, their light pushed deep into the infrared by billions of years of travel. Many had never been recorded by any instrument before. What made the image remarkable wasn't just what was in it. It was the comparison it allowed. Hubble had stared at that same patch of sky for 11 days straight and captured faint, structureless smudges at the very edge of its ability to see. Webb reached the same depth and well beyond it in a fraction of that time. And where Hubble had shown smudges, Webb showed structure, spiral arms, bright galactic cores, visibly different colors marking different stellar populations. It wasn't a better photograph. It was a fundamentally different kind of seeing. And buried inside that very first image, before any of Webb's dedicated science programs had even begun, was something quieter than a discovery, a warning. A handful of the faintest galaxies in the frame didn't quite match what current models said they should look like at that distance. Too bright, too structured, too early. Nobody was ready to call it a crisis yet. The dedicated surveys hadn't even started. The real test came from a set of programs designed specifically to stare into the same patch of sky for hundreds of hours, hunting for the faintest and oldest galaxies anyone had ever tried to find. The most ambitious of these was called JADES, the James Webb Advanced Deep Extragalactic Survey, led by a team from Harvard alongside researchers from the University of Arizona and UC Santa Cruz. It targeted two regions of sky already mapped by Hubble, using years of existing data as a baseline for comparison. The numbers tell you how far the gap had grown. Hubble spent roughly 400 orbits and 11 days of total exposure to produce its deepest image, reaching back to galaxies that existed 500 to 800 million years after the Big Bang. Webb could match that same depth in a fraction of the time. And unlike Hubble, it could take a full spectrum of each galaxy, not just a faint smudge of color. A spectrum doesn't just confirm that a galaxy is far away. It tells you exactly how far, by measuring the precise wavelengths of light stretched by the universe's expansion. No more estimating from color alone. In January 2023, the first spectroscopic results came back. A team led by a researcher at the University of Hertfordshire confirmed 4 galaxies sitting between 300 and 450 million years after the Big Bang, the most distant galaxies ever directly measured at the time. These weren't faint smudges sitting exactly where the models expected. Several were bright, structured, and carrying more total starlight than the standard model of galaxy formation said should exist that early. That standard model is called lambda cold dark matter, refined over 4 decades of observation and simulation. It describes a slow, patient universe. Small clumps of dark matter gradually pulling in gas slowly cooling into stars, structure building piece by piece over hundreds of millions of years. Webb's first confirmed galaxies didn't behave like that. As more surveys came in throughout 2023, the pattern only got stronger. A team at the University of Texas at Austin cataloged hundreds of candidate galaxies from the universe's first 650 million years and found bright galaxies at the most extreme distances, appearing roughly 10 times more often than any model predicted. A parallel effort called Cosmos Webb mapped an even larger area of sky, eventually cataloging close to 800,000 galaxies across 98% of the universe's entire history. As that dataset grew, its lead researchers said plainly what many in the field had been thinking privately. The data wasn't just challenging the model. It was persistently, consistently at odds with it. Then came the objects researchers started calling, half seriously, the universe breakers. In February 2023, a team from Swinburne University in Australia identified 6 galaxies formed within the first 500 to 700 million years of cosmic history, each containing somewhere between 10 billion and 100 billion times the mass of a typical star, in stars alone. For comparison, the Milky Way, considered a large galaxy by modern standards, contains roughly 60 billion stellar masses. These 6 objects, formed when the universe was less than 5% of its current age, were already in the same weight class. To build that much mass that quickly, a galaxy would need to convert almost every available atom of gas directly into stars, continuously, from the very first moment it began forming. An efficiency that known physics says should be essentially impossible. Later follow-up observations added a complication. In some of these galaxies, part of the apparent stellar mass turned out to be light from actively feeding black holes, not starlight, meaning the original estimates had been somewhat inflated. But even after every correction, the population of overly massive early galaxies remained roughly 10 times larger than the standard model allowed. The crisis had shrunk. It hadn't disappeared. Then, in May 2024, came a discovery that pushed the timeline to its absolute limit. A team confirmed the most distant galaxy ever directly measured, catalogued as JADES-GS-Z14, with light that left it just 290 million years after the Big Bang. At that point, the universe was only 2% of its current age. This wasn't a faint smudge. The galaxy stretched over 1,600 light-years across and contained hundreds of millions of stellar masses worth of stars. Researchers noted they could have detected this same galaxy even if it had been 10 times fainter, meaning objects like it, or larger, might be sitting even further back in time, waiting to be found. Then, in March 2025, a follow-up observation combining Webb with a radio telescope array in Chile detected something inside that same galaxy that turned the discovery into something far stranger: oxygen. Oxygen isn't primordial. The Big Bang produced almost nothing but hydrogen and helium. Every atom of oxygen in the universe is forged inside a star and released only when that star dies. Meaning for oxygen to exist in this galaxy, an entire generation of massive stars had to form, live out their full lifespans, and explode before a second generation could even begin. All of that, first ignition, complete stellar lifespans, supernova enrichment, a second generation rising from the wreckage, had to happen within 290 million years of the Big Bang. Under the models that existed before Webb, that window was barely enough time for the very first stars to switch on at all, let alone die and seed a whole new generation behind them. The researcher who led the discovery called it completely unanticipated. It's hard to find a more accurate description. Something in the early universe was working faster and more efficiently than any equation currently on the books can explain. And the galaxies weren't the only things arriving early. At the center of nearly every one of them, something else was growing far faster than it should ever have been allowed to. At the center of nearly every large galaxy in the universe, including our own, sits a supermassive black hole. The one anchoring the Milky Way carries roughly 4 million times the mass of a typical star. Their presence is so routine that astronomers build one into the model of almost any large galaxy they study. Our own galaxy's black hole isn't doing much right now. It feeds on scraps, the occasional drifting cloud of gas, the rare star that wanders too close, a quiet remnant sitting at the center of a quiet galaxy. It wasn't always this calm. And the deeper Webb looked into the past, the less calm it found. Growing a black hole to that scale takes time. A black hole forms small, usually from the collapsed core of a single massive star, and has to feed its way up to millions or billions of solar masses over a very long stretch of cosmic history. There's a physical speed limit on that process, known as the Eddington limit. It describes the maximum rate at which a black hole can pull in surrounding gas before the radiation generated by that infalling material pushes the rest of its fuel supply away, even feeding at that maximum sustainable rate without interruption. Growing a seed black hole up to 100 million or a billion solar masses takes hundreds of millions of years and requires near-perfect conditions the entire time. Think of it like trying to fill a swimming pool through a straw that can only handle so much water before it bursts. No matter how patient you are, there's a ceiling on how fast that pool can fill. And the universe, under the standard model, simply hadn't had enough time to reach that ceiling this early. Webb kept finding black holes of that size far earlier than the timeline should allow. In 2024, a team at Cambridge confirmed a black hole at the center of a galaxy sitting roughly 400 million years after the Big Bang, already carrying about 1.6 million solar masses, and actively pulling in roughly one star's worth of material every 5 years. A separate detection, combining Webb with the Chandra X-ray Observatory, found a black hole of 10 to 100 million solar masses at an even earlier point, only about 450 million years after the Big Bang. Less time, more mass. The math kept getting harder to make work. But the deeper version of this problem came from a population of objects that earned their own nickname: little red dots. A team at the Institute of Science and Technology Austria cataloged them systematically in 2024. Compact reddish objects with a distinctive spectral shape that set them apart from anything seen in the nearby universe. Their black holes range from 1 million to 100 million solar masses. On its own, that's not unusual. What made them strange was how much of their host galaxy that mass represented. In the present-day universe, a galaxy's central black hole typically accounts for about 0.1% of its total stellar mass, a relationship that holds remarkably steady across thousands of galaxies. In the little red dots, that ratio climbed to 30% or higher, roughly 300 times the normal proportion. These weren't small galaxies with modest black holes. They were black holes that nearly outweighed the entire galaxy supposedly hosting them. 341 of these objects have now been cataloged, appearing at a period roughly 600 million to 1.3 billion years after the Big Bang. 10 to 100 times more common than any model predicted. 3 competing explanations have been proposed. None of them fully close the gap. The first involves something called direct collapse. Under specific conditions in the dense, radiation-filled early universe, A cloud of primordial gas could in theory collapse directly into a black hole, skipping the stellar phase entirely, and being born already carrying tens of thousands of solar masses. That would give a black hole a serious head start. But producing direct collapse black holes in the numbers needed to explain the cataloged objects stretches the mechanism well past its comfortable limits. The second explanation requires black holes to grow faster than the Eddington limit allows. This isn't impossible in principle. Simulations show that under the right conditions, a black hole can temporarily exceed that rate by several times. But the little red dots appear to need sustained excess growth over hundreds of millions of years, far longer than any simulated episode has ever produced. There's also a contradiction built into this explanation. A black hole feeding that aggressively should generate enough radiation to blast away surrounding gas and shut down star formation nearby. Yet these objects show clear evidence of active star formation happening at the same time, right next to an engine that should be destroying the very conditions that allow it. The third explanation has fewer supporters, but is harder to dismiss outright. It involves primordial black holes, objects that may have formed directly from density fluctuations within the first second after the Big Bang, long before any star existed. They've been theorized for decades, partly as a candidate for dark matter itself. If they existed in large enough numbers, they would provide seeds for galaxy-building black holes far more massive than any dying star could ever produce, skipping the entire slow climb through stellar collapse and Eddington-limited feeding altogether. It's the most radical of the three explanations, because it would mean some of the universe's largest black holes never really grew in the conventional sense at all. They simply started big before a single star had ever switched on. The problem is that no direct observational evidence for primordial black holes has ever been confirmed, and nothing in current theory tightly constrains how many of them there should be. What's left is a population of objects that researchers openly admit they cannot fully explain. 341 little red dots, each hosting an engine that outweighs its own galaxy by a margin observed nowhere in our cosmic neighborhood. 10 to 100 times more common than expected, and not one leading theory accounts for all of it on its own. Follow-up observations in 2025 added yet another wrinkle. Some objects in this category were found to be producing far more ultraviolet light than a black hole's feeding disk alone could account for, suggesting the surrounding stars were contributing more to the signal than first thought. The line between black hole light and starlight in these objects turned out to be far blurrier than the original classification implied. The early universe, it turns out, built its most extreme objects first, its biggest galaxies, its fastest-growing black holes, long before it built anything resembling the calmer, more spread-out cosmos we see around us today. If that's true, then the quiet neighborhood we currently call home, with its dormant black hole and its slow, orderly galaxy, may not be the universe's natural state at all. It may simply be what's left over after the chaos burned itself out. And these objects weren't isolated cases scattered randomly through space. They were part of something far larger, a structure spanning the entire observable universe, one that comes with its own set of rules about how big something is allowed to be before it shouldn't exist at all. Zoom out far enough from any single galaxy, any single black hole, and the universe stops looking like a scattering of random points. It starts looking like architecture. Galaxies aren't spread evenly through space. They cluster along thread-like structures called filaments, some stretching hundreds of millions of light years, with dense knots where multiple filaments intersect and vast, nearly empty gaps in between. Together, this network is known as the cosmic web, the largest coherent structure in existence. It formed because the early universe wasn't perfectly smooth. Tiny variations in density, present from the very first fraction of a second after the Big Bang, were slowly amplified by gravity over hundreds of millions of years. Matter fell inward along these invisible channels, building up where they crossed and emptying out everywhere else. Most of what holds this web together is dark matter, invisible, undetectable directly, traced only through its gravitational pull on the galaxies and light that move through it. Ordinary galaxies are just the bright decoration sitting on top of a much larger, unseen skeleton. A single filament connecting two galaxy clusters can stretch 100 to 300 million light-years and carry more total mass than thousands of individual galaxies combined. And almost none of that mass gives off any light at all. Webb added something previous surveys couldn't: depth. By tracing the structure back into the early universe, researchers found galaxy clusters already linked by clearly defined filaments, at a stage when, according to the Standard Model, large-scale structures should still have been in its infancy. The scaffolding was going up earlier than anyone expected. One more thread in the same pattern running through everything else this telescope has found. But a web isn't just made of threads. It's also made of gaps. And some of those gaps are large enough to break intuition entirely. The biggest confirmed example sits in the direction of the constellation Bootes, discovered back in 1981 during a routine survey of galaxy distances. Astronomers expected some variation in density across the survey. Clusters in some places, emptier patches in others. What they found instead was a region roughly spherical, around 330 million light-years across, containing only about 60 galaxies, where models predicted there should be thousands. The astronomer who found it reportedly said he was embarrassed to tell people how empty it was. Here's what that scale actually means. If our own solar system sat at the center of that void, in the exact position it occupies today, we wouldn't have confirmed the existence of other galaxies until decades later than we actually did. The nearest galaxies beyond our own would have been too far beyond the reach of early 20th century instruments to detect at all. An entire chapter of astronomical history. The moment humanity first realized the universe was unimaginably larger than one galaxy would have been delayed by half a century, simply because of where we happen to be standing. That single fact reframes everything about how we read the universe from our own position in it. Your address inside the cosmic web doesn't just affect what you can see, it determines what you can know. Which raises an uncomfortable question much closer to home. A growing body of evidence suggests we may be living inside a void ourselves, just a far larger, far gentler one. Researchers identified it in a 2013 study and named it after their initials, the KBC void. An underdense region roughly 2 billion light-years across, with our own galaxy sitting well inside its boundary rather than near any edge. 2 billion light-years is 6 times the diameter of the Bootes void, the same void so empty its discoverer was embarrassed by it. Inside the KBC void's boundaries sits our entire local supercluster. The dense concentrations of matter we're gravitationally flowing toward, and hundreds of millions of light-years of surrounding space in every direction. This isn't just a curiosity about geography. It connects directly to one of the deepest unresolved problems in modern cosmology. Matter inside an underdense region experiences gravity differently than matter in an average one. Galaxies near the edges of a void tend to get an extra outward push, pulled toward the denser walls surrounding them as the void itself slowly empties further over time. If our position inside this void is adding a small systematic boost to the velocities of nearby galaxies, then any measurement of cosmic expansion taken from inside it could read differently than the true global rate. Not because the instruments are wrong, but because we'd be measuring the universe from inside a bubble, and the bubble would be quietly distorting the number. Whether the KBC void fully explains the discrepancy that comes next is still genuinely contested, but it's no longer dismissed as irrelevant. Our address in the universe is not a neutral fact. It's a physical circumstance with measurable consequences for the numbers our most precise instruments hand back to us. That address has a name too. In 2014, a team led by a researcher in Hawaii formally mapped the supercluster containing our own galaxy for the first time, using a catalog of galaxy velocities rather than simple positions, tracking not just where galaxies sit, but where they're headed, and reconstructing the gravitational landscape that explains their motion. They called the resulting structure Laniakea, a word meaning immeasurable heaven. Laniakea spans roughly 500 million light-years and contains more than 100,000 galaxies, all gravitationally bound into a single flowing structure. The Milky Way sits near its outer edge. A follow-up study in 2023, using an expanded version of the same velocity catalog, confirmed the supercluster's boundaries and found that structures like it across the local universe tend to run roughly 10 times larger than the standard cosmological model predicts they should. And the entire structure, every one of those 100,000 galaxies, our own included, is slowly flowing inward, drawn toward a dense concentration of mass in the direction of the constellation Centaurus, known as the Great Attractor. Beyond it lies something even larger, pulling everything toward it in turn. The Shapley concentration, the densest known accumulation of galaxies in our local universe. Matter flows toward density the way water flows downhill. And on the largest scales we can measure, we're still being pulled somewhere. So the universe isn't just stranger up close, in its earliest galaxies and its overgrown black holes. It's stranger in its architecture too, riddled with gaps too large to explain, built around a structure that places our own galaxy inside one of them, and flowing toward attractors so massive they bend the trajectory of everything within 500 million light-years. And that architecture turns out to be more than a question of geography. It may be the missing piece in an argument that has been splitting cosmology in two. For over a decade, cosmology has been stuck on a single number it can't pin down: how fast the universe is actually expanding. It sounds like it should be simple. Point your instruments at the right targets, measure how quickly galaxies are receding, and you get a rate. But there are two completely different ways to arrive at that number, using two completely different eras of cosmic history. And they refuse to agree. The stakes for getting this right go back to 1998, when researchers discovered that the universe's expansion wasn't just continuing, it was speeding up. That finding introduced the idea of dark energy as the dominant force in the cosmos, and earned its discoverers a share of the Nobel Prize in Physics in 2011. Ever since, pinning down the precise expansion rate has been one of the central goals of observational cosmology, because that single number underpins almost everything else we think we know about how the universe has evolved. The first method looks at the oldest light there is, the cosmic microwave background, the faint afterglow left over from the Big Bang itself. By analyzing the tiny patterns frozen into that radiation, researchers can calculate what the expansion rate should be today, extrapolated forward from the very beginning. That method consistently lands around 67 kilometers per second for every additional megaparsec of distance. The second method works in the opposite direction, building outward from our own cosmic backyard. It starts with nearby stars whose distances we can measure directly, climbs up to a class of pulsating stars in nearby galaxies whose brightness reveals their distance, and climbs again to exploding stars bright enough to be seen across billions of light-years. Each rung calibrates the one above it. This method, refined over more than a decade by a team that later won a share of a Nobel Prize for related work on cosmic acceleration, consistently lands closer to 73. 67 versus 73 doesn't sound like a dramatic gap. But both numbers come with remarkably tight error bars, and once you account for that precision, the disagreement stops looking like noise and starts looking like a 5 to 6 standard deviation discrepancy. A level of statistical confidence that, in physics, normally means you found something real, not something you can blame on a bad measurement. In particle physics, a 5 sigma result is the standard threshold required before a new discovery is officially announced. The Hubble tension cleared that bar years ago, and the gap has only become more precise, not less, with every new dataset added since. For years, the working assumption was that better instruments would eventually make the gap close on its own. Some unaccounted source of error, somewhere in one of the two methods, would get identified and corrected, and the numbers would converge. Webb was supposed to be the instrument that settled it. Its sharper resolution meant it could reobserve the exact same nearby stars that had been used to build the local distance ladder in the first place, checking whether Hubble's older measurements had been subtly contaminated by crowding or instrumental error. If the discrepancy really was just a measurement problem, this was the moment it should have started to disappear. It didn't. When the results came back in 2023, Webb's measurement of the local expansion rate matched the earlier value almost exactly. Instrumental error, one of the most plausible explanations on the table, had just been effectively ruled out by the most precise telescope ever built. That's a heavier result than it might first sound like. For years, better data will fix this had been the most comfortable answer available, the one that let cosmology's foundations stay intact while a single measurement got sorted out. Webb was supposed to provide that better data. Instead, it confirmed there was nothing left to sort out on the instrumental side at all. A separate team, led by a researcher at the University of Chicago, using entirely different methods to measure stellar distances, including the natural brightness ceiling reached by aging red giant stars and a different class of pulsating stars altogether, found a more complicated picture. Two of their three independent techniques landed closer to the early universe number. Their conclusion was that some kind of systematic error likely remained somewhere in the chain. But the team that had spent over a decade refining the local measurement held their ground, maintaining the discrepancy was real, not an artifact waiting to be found. The field as of now has no consensus. What it does have, confirmed by an instrument with no real margin for instrumental doubt, is a genuine unresolved crisis sitting at the very foundation of how we measure the universe. This is where the void from earlier in this story stops being a side note and becomes a real candidate explanation. If our galaxy sits inside a large underdense region, as the evidence increasingly suggests, then galaxies near us would be getting pulled outward by the surrounding denser walls, adding a small extra boost to their measured velocities. Every local measurement of expansion, built from exactly these nearby galaxies, could be quietly inflated by that effect. While the early universe measurement, drawing on light from the entire observable cosmos, wouldn't be affected at all. It's an elegant explanation, and it might account for some of the discrepancy. Whether it accounts for all of it is still an open question. Some analyses suggest the underdensity isn't quite pronounced enough to close the entire gap on its own. Others find that once its effect is properly modeled, what's left over could fall within the range of ordinary remaining error. Either way, the disagreement itself is no longer something cosmologists expect to quietly resolve. Two of the most precise measurements ever made, both checked and rechecked, both surviving the scrutiny of the best instrument ever built, are telling us two different things about the same universe. And neither one is wrong in any simple, fixable sense. What makes this particular crisis different from the others in this story is what it implies about the tools themselves. The expansion rate isn't just one number among many. It's baked into nearly every other calculation in cosmology. The age of the universe, the distances to the galaxies Webb has been photographing, the timeline behind every overgrown black hole and impossibly massive early galaxy. If the expansion rate itself depends on which method and which era of cosmic history you choose to trust, then a layer of uncertainty runs underneath everything else this telescope has found. And the expansion rate isn't even the deepest unresolved question. Behind it sits a much stranger one, about the force actually driving that expansion in the first place, and whether it has been quietly changing this entire time. Whatever is driving the universe's expansion makes up roughly 2/3 of everything that exists. We call it dark energy. And until recently, almost everyone assumed it was simple. The standard assumption, going back to a term Einstein originally inserted into his own equations and later regretted, treats dark energy as a constant. A fixed energy density built into empty space itself, pushing outward with exactly the same force no matter where or when you measure it. It doesn't strengthen. It doesn't weaken. It just is. Everywhere. Forever. In April 2024, a survey instrument mounted on a telescope in Arizona released results that put that assumption under serious pressure. Over its first year of operation, it had measured the redshifts of more than 6 million galaxies, building the most detailed three-dimensional map of the universe's large-scale structure ever assembled. When that map was combined with data from the cosmic microwave background and a separate catalog of exploding stars, the result didn't match a constant. It showed a deviation from the simplest model at a confidence level just under 4 standard deviations. Not yet the gold standard for a confirmed discovery, but far too strong to dismiss as noise. A follow-up analysis published in 2025 sharpened the picture further, finding that dark energy appeared to have weakened by roughly 10% over recent cosmic history, at better than 99% confidence. The force assumed to be the one truly unchanging quantity in the universe might not be unchanging at all. This matters more than almost any other number in this story, because the long-term behavior of dark energy isn't just one variable among many. It's the variable that decides how everything ends. The leading alternative to a simple constant is a hypothetical field that evolves slowly across cosmic time, strengthening or weakening as the universe ages, arising naturally from certain extensions of particle physics. The trouble is that to match what's actually been observed, this field would need to have stayed essentially motionless for the first 10 billion years of cosmic history, only beginning to shift meaningfully in the last few billion. Nothing in existing theory explains why it would behave that way. There's a more specific wrinkle buried in the data too. Physicists describe it using a single parameter that captures how dark energy's pressure compares to its density. For a true constant, that parameter sits at exactly -1. Values above it describe a force that gradually weakens over time. Values below it describe something stranger, a category nicknamed phantom energy, which grows stronger the more the universe expands, accelerating the expansion further in a feedback loop with no natural ceiling. The newest analysis suggests dark energy behaved like phantom energy in the past, then crossed back above that threshold and has been weakening ever since. That crossing is the strange part. The simplest theoretical models, including the basic cosmological constant, aren't allowed to cross that line at all. They're stuck on one side of it permanently. The data appears to be describing behavior the simplest physics says shouldn't be possible. Which brings us to the ending. Or rather, the three of them. Because right now, the available evidence can't eliminate any of them. The first is the one cosmology had settled on for roughly 2 decades: heat death, sometimes called the Big Freeze. If dark energy stays constant or weakens too gradually to matter, the universe simply keeps expanding forever, growing colder and emptier. Galaxies beyond our immediate neighborhood drift past the point where their light can ever reach us. The stars that remain slowly exhaust their fuel and go dark, one by one, over spans of time that make the current age of the universe look instantaneous by comparison. Eventually, nothing changes again, because nothing is left that can. The second is the Big Rip. The ending implied if dark energy's phantom behavior wasn't just a brief phase in the past, but a preview of where it's headed again. Under this scenario, the repulsive force keeps strengthening without limit as space keeps expanding, until it grows strong enough to overpower every other force in nature, one structure at a time. Galaxy clusters lose their grip on each other first, then individual galaxies, then solar systems, then planets. In the final, almost incomprehensibly brief stretch before the end, even atoms are torn apart, pulled open by a force that no longer recognizes any bond as strong enough to resist it. The third returned to serious consideration only recently, revived by a 2025 paper proposing that the cosmological constant might not be a fixed, permanent value at all, but a temporary state. Currently positive, but built on a foundation that is, at its deepest level, negative. Under this model, today's accelerating expansion is a phase, not a destination. It continues for roughly 11 billion more years before gravity finally regains the upper hand and the universe begins to contract. Slowly at first, then faster. The sky brightening instead of darkening as everything that has ever expanded outward gets pulled back together, ending in a collapse back into the same kind of singularity the entire universe once expanded out of. A cold, eternal silence. A violent unraveling that ends with atoms themselves coming apart. A total collapse back to the beginning. 3 futures, each one complete, each one final. And none of them currently ruled out by anything we've measured. What ties this back to everything covered here is simpler than it sounds. The same telescope that found galaxies too massive to exist, black holes too early to have grown the normal way, and a void large enough to reshape what an entire civilization could know about its own universe. That same telescope pointed at the question of how this all ends, came back with 3 answers instead of 1. We happen to exist at a moment when the universe's history is still legible, when the oldest light is still detectable, when the expansion is still measurable, when the disagreement between our instruments can still be investigated rather than simply accepted. That window won't stay open forever. Galaxies are already slipping past the horizon where their light will never reach us again. And the evidence available to read this whole story will eventually run out for anyone who comes looking after we're gone. So the discomfort here was never really about scale. We already knew the universe was big. What Webb actually revealed is that our confidence in understanding it was premature, and that the most basic questions anyone could ask, how it began and how it ends, are, after everything we now know, still genuinely scientifically open. In 2022, the James Webb Space Telescope captured images of galaxies that formed when the universe was